Okay, guys. So let's keep going with transverse weight shifts. It's relatively short, and after that we'll do two examples which should help with the homework. Okay, so all right. Last time we started talking about what happens if we move a huge container from one edge of the ship to the other edge, and intuitively we can see that the hull will start heeling slightly. It'll tilt slightly. And the main thing we'll try to do is try to find that angle, the heel angle. Okay, so let's draw this again in a slightly tilted state here. Before moving the weight, let's say G was here and M is here. And again, for small angle changes, the meta center does not move a lot. So we can assume that it remains fixed. And this is G1.
Hold on, what do you mean by small angle changes on the meta center? I thought it was always fixed.
Say that once more.
I thought the meta center was always fixed and based on the shape of the hull.
No, if you look back to how we computed the meta center, it depends on the submersion.
Oh, that's right. So as you tilt, the whole shape changes and then, okay.
Yeah, exactly. So for small angles, we can assume that the change is not huge. So the meta center stays fixed.
That's right. That's right.
If the heel angle is more than 10 degrees, then we cannot use this assumption anymore.
But okay, so say the hull was like a canoe where it just didn't change at all as you tilted it.
With a canoe, it wouldn't change if you tilted just less than 10 degrees.
Okay.
Yeah. So when we've moved the container to the right, we've also shifted our center of gravity from G0 somewhere over here. And this angle, the heel angle, we call phi. So we need to find, the first thing we need to do is we need to find, oh, I already wrote that. We need to find the shift, lateral shift in the center of gravity location. So lateral shift in CG is the distance G0, G1. When I write G0, G1, I don't mean G0 times G1. I'm just talking about the distance G0, G1. Okay, and we already have done this many times, combined two different objects, combined center of mass, combined centroid. We do the same thing again. So so first, let me point out that we measure transverse coordinates that's the y coordinates from the center line. Okay, and then CG1, CG0, CG little one, CG0, etc. to denote the transverse coordinates. All right, so can you think of how we should set this up? What we need is CG1. How should we write this? Is equal to what? Think about composite mass. What have you done? You've subtracted mass from the left edge, added mass on the right edge. Do you remember this? YCG is M1, Y1 plus M2, Y2 plus dot dot dot. See, we keep writing the same type of formula, for whether it be for mass, for area, or for volume. So always think of that. So what should we write for CG1? No ideas? What should we take M1 to be? Mass 1? Okay. Nobody? Then take a guess. What should mass 1?
The weight of the ship?
Yeah, we can take mass 1 to be the weight of the hull. Okay. So we can say this is delta 0 over G. Remember, delta 0 is in Newton. So just divide that by G to get the mass. Okay, and Y1 is CG0. Yeah, the center of mass for the hull would be CG0 initial. Okay, then what? Plus or minus? Let's talk about the mass we have removed. Minus or plus? And what's the mass? We remember how we did this for area? We were cutting area out and moving to the other place. We do the same thing here. So we take a container, move it to that side. What's the next? Do we?
So you would subtract the weight of that mass at that position?
Yeah, so we do a negative mass is weight over G, and that position we'll denote it by CG0. So CG0. Okay, and then since we've put that mass over here, that means like we've added the mass. So plus W over G, C little g1. Okay, and on the bottom we just have delta 0 over G minus W over G, W over G. Is that good?
Yeah, I'm sorry. Can you clarify where C is again? Is that the center of buoyancy?
No, it's the center line.
The center line. Oh, that's so that's
Yeah.
a distance.
Yeah, and anytime we talk about the Z coordinate, we start at K. So we write Km, Kg0. When we talk about the transverse coordinates, we'll start at the center line, go left or right.
I see. Okay.
All right. So These two go away. And when we rearrange this, we get CG1 minus CG0 is equal to delta delta cancel W CG1 minus CG0 over delta 0. I've just rearranged things. Okay, and what is this? This is W times G1 G0 divided by delta 0. G1, G0, we know because we were told that we've moved the mass h units. So this is equal to whatever we are told the movement is. Okay, and CG1 minus CG0, this is basically G1, G0, right? That's the distance. If you take coordinates of CG1 and subtract CG0, we basically get the distance G1, G0. All right, so that's a useful one to remember. G1, G0 is equal to W dot G1, G0 over delta. And if we try to relate this to the roll angle, and phi is related to this as phi is tan inverse G0, G1, G0, M. Okay, that's just trigonometry. Tan inverse G0, G1 over G, because we have a right angle triangle here. So G0, G1 we just computed, and G0, M we knew from the original configuration. So you can compute the roll angle. Right. Okay. So G0, G1, we can substitute. You have W dot G1, G0 over G0M times delta 0. Okay. So anytime you shift weights, that's how you would compute the heel angle. Any questions? Great, let's do the first example. Just a reminder, don't forget about midterm on Wednesday. Okay, so we're given a rectangular pontoon that's floating on even keel. When you see the term even keel, that just means there's no list angle and there's no trim angle either. So perfectly level. All right, so we have a rectangular pontoon, and we're told there's a container already on board, which we move transversely. After moving it, the change in the center of gravity location is given here. And we are asked, what is the angle of heel? And what was the weight that was moved if it was moved 5 meters? Okay, so the first thing you should always do is draw sketches to put down all the information given to you. And so let's draw a top view. All right, so we're told the beam is 6 meters, so this is given to be 6 meters. Length is 36. Draft is 2 meters. Kg is 1.9, so we have keel here, G somewhere here. Okay, let's see, is there something else we can use? No. Okay, so transverse change in CG is 0.1. Okay, so let's draw what happens with this movement. Yeah, I should have drawn a perfect rectangle since it's a rectangular pontoon. Okay. Resulting transverse change in CG is 0.1, blah, blah, blah. What is this telling us? 0.1058. On the sketch, what does this tell us?
The new center of gravity moved over to the right, 0.1 meter.
Exactly. So this G0 was the initial center of gravity. Now we just moved it to the right. So this would be the G1 location. And we're told this is equal to 0.1058 meters. All right. And the thing we don't know is this heel angle phi. How would you find this unknown angle? How would you find the unknown angle phi? We know this dimension. We need just one more thing. What do we need?
The height of the metacenter?
Yeah, we just need the metacentric height from, we basically need G0M. So to compute phi, we would just have tan inverse G0 G1 over G0 M. Okay, and remember for small angles, sine and tan, they're equivalent to the angle itself in radians. Okay. You don't have to do this. You can use the tan inverse function on your calculator. But you'll see for small angles, the answer is basically the same. Okay, so G0, G1 is given to us. This is given to us 0.1058. G0M, we don't have. Do you know how to compute this? You remember how to compute G0M? We did examples and in previous classes. That's the initial stability. Whenever we were asked, we would have to compute G0M. So to do that, the same way you did it for the previous examples, you would do Km is equal to Kg0 plus G0M. G0M is Km minus Kg0. Okay. Kg0 is given. This is given to be 1.9 meters. And this guy, we don't know yet. Okay. And to compute that, you can just use Km is Kb plus Bm. Kb is, if it's a rectangular pontoon, you know how to compute Kb. It would just be 1 meter. So Kb would be 1 meter. And Bm is I over nabla. Okay, and the same thing we did in the last class. You know how to compute the I, you know how to compute the nabla. So you have everything you need to compute the phi. Is everybody good on Kb is equal to 1 meter? Only if this is a perfectly rectangular cross section. Otherwise, not true. Is half of the draft. Okay, so
Yeah, that makes sense.
All right, perfect. Any questions here? I mean, there's not much to do here. You basically just have to crunch numbers. Okay, so let's try the next part of the problem. Next part says weight. So delta container is what? If shift is 5 meters. Okay, so we're told basically this movement was a 5 meter lateral change. And to figure this out, we can use the formula we just derived here. So let me shift here. I'll rewrite this formula down here. So phi is okay, and this W is basically what we're asked for. So this is the delta container. G0, G1 is given. This is 5 meters. G0M we computed in part A. What is delta 0? This phi angle also we computed in part A. Okay, so the only thing that's we don't seem to have at the moment is the displacement of the hull. How do you compute that? Is all of this making sense?
Yeah, I'm not sure how to do the delta 0.
Okay, okay. So delta 0 is what? The weight of the hull, okay? Always think about, okay, if I want to compute the weight of something that's floating, I should think about getting the volume that it displaces. So let's look at the sketch. Can we figure out the volume that it displaces?
Yes.
2 times 36 times 6. Does that give us the volume of the hull only?
Of the displaced volume.
Of just the hull, or so?
Of the container too.
Correct, exactly. So this 6 times 36 times 2 will give us container plus hull, okay? So to compute delta 0, we can use the known combined displacement. Volume displacement. So nabla combined is nabla hull plus nabla container. And this we know is L times B times T. And that's given, okay? So delta combined we know is rho G nabla combined. So this is rho G rho G times LBT, and delta combo is delta hull plus delta container. So here you have delta 0 is rho G LBT minus delta container. That's what we were missing. So you can plug this in here. Delta 0 gets replaced by rho G LBT minus delta container. And now we only have one unknown in this equation, delta container on top, delta container on the bottom. And you can solve that easily. Okay. Any questions?
Didn't it ask for the mass of the container?
Yeah, so this is what we were asked for, delta container. Here in this equation, we know everything. We know the angle, we know G0M, we know G1, G0. We don't know the weight of the container. So, that's the unknown, W, or delta container. And delta 0, we just rewrote as rho GLBT minus delta container. So this equation you can use to compute delta container and divide that by G to get the mass.
But wouldn't you need to know like density of the container too? And
Density of the container? No, you don't need to know the density of container. This is rho of seawater, right?
so you're saying delta container is in units of mass?
No, this is weight.
Weight, okay.
Yeah, delta is always weight. So mass of container would be.
I see. I need to divide by G.
Yeah. Did I say
Okay.
rho? Yeah, it's just divide by G.
Okay, thanks.
Yeah, so this equation is fairly easy to solve. Everything's known except for delta container. Any other questions? Okay, so let's do another example where we load and unload weight or cargo on the ship. So example, weight loading and unloading. So I'll make a table of the weight and the position they're put in. So weight loaded. So we have containers of different weight, either being loaded onto the hull or being discharged. And the positions are kgi in meter. So remember, whenever we talk about the Z position, we start at the keel. So this is 8.0, 2.0, 6.0, 1.5. That gives us one of the coordinates. We also need to know the transverse position. So we also need CGI. We're told 5 meters port, 6.5 meters starboard, 2.0 port, 3.0 port. So knowing whether you put it on the port side or the starboard side is important because that gives us the plus or minus Y location. And yeah, let me just write out KGI is vertical location of CG, and CGI is transverse. Okay, and we're also given other information. Delta is 10,000 ton before loading / unloading. So that was the combined displacement with the hull plus initially placed cargo. before we started putting on extra stuff or removing containers. And we're also told kg0 is 7.5, g0m 1.5, phi 0 is 4 degree to port. Okay, so before we even started moving stuff, there was non-zero heel angle, list angle of 4 degrees. Right, and we're told that the ship does not trim. What does that mean, does not trim? Trim angle is the static pitching angle. Okay, so the ship is perfectly level in the longitudinal direction. There's no angle this way. Okay, so the question makes sense. We have some initial conditions given for the hull, and the table says we add on containers or remove containers at particular locations. What happens to the list angle is the question. Does it get greater than 4 degrees? Does it decrease? Or does it remain the same? So we draw, again, let's draw a sketch. And we're not told the cross section is rectangular, so we cannot assume anything. So this is the front view. All right, so let's also mark what else we're given. We're given kg0 is 7.5. And G0M is 1.5. So of course, not drawn to scale. Just using trigonometry, you already see we can compute G0, G1 very easily. So we use this is the initial state of the hull. This is before we have done any loading or unloading. So once we start loading and discharging cargo, the ship's state will change from this initial condition shown here. There are two things that will happen to the G. It will move up or down as well as laterally. The reason for that is because you're adding extra cargo or removing extra cargo. So you, depending on where, if you place everything at the deck, you expect G1 to move up along vertically slightly. You place everything in the hold right at the bottom, you expect G1 would move down slightly. Also, if you load everything on the right, on one edge, you'd expect G1 to move laterally in that direction. So we need to determine both of these shifts, both the vertical shift and the lateral shift. So we first need to compute both the vertical and lateral shift in the location of G1. All right, and let me draw a sketch of what it would look like in the final state. So this is the initial state. Let me just mark this initial state. Okay, and I'll try and draw a sketch of the final state. M location unchanged. We're told so in the problem. And let's say the final tilt angle is phi final. We don't know what it is right now. That's what we need to compute. And the two
Just
x's I've marked.
1 second. How can M not change since we did a net loading and added more weight to the craft?
Let me think. Will loading make a big difference? It will if you change it substantially, but let's see. Here, the net loading turns out to be 900, so 10%. So delta would change slightly. Okay. Yeah. So if the change in displacement is substantial, M would change, but in the problem we're told M remains fixed. Let me get rid of this small angles qualifier. Okay, so Km basically remains at 9 meters, 7.5 plus 1.5. All right, so this phi final that we're trying to find, so phi final is basically tan inverse of CG final over G final M. I'll just mark it CG final Y and G final Z M. So CG final, remember, gives us the lateral displacement from the center line. So that's basically this base of this triangle here. And G final M is the other side of the triangle. Okay, so those are the two things I need to compute this unknown new angle. All right, so our G1, we've assumed it goes up, and we don't know whether it'll go up or down. If we get a negative number, we know it'll shift down. If we get a positive number, we know it'll shift up. So our G1 has shifted to this G final position, and the corresponding horizontal location on the center line I've marked as G final Z, and the G final itself are marked as G final Y. All right, so how do we compute this shift in G1 to G final using the info given here? So what would you? Okay, so don't give me the whole answer, but think about how we approach this. How do we compute change in the shift in center of mass or center of gravity? No? How did you compute change in shift here when you moved one container from left to right? You use this. We'll use the same thing over and over, okay? So Z coordinate of G final is kg0 delta 0 plus kg1 delta 1 plus kg2 delta 2 minus kg3 delta 3 minus kg4 delta 4. Same thing, mass 1. So of course I should divide everything by G, but all the G's would cancel out on top and bottom. So you can write the divide by G's if you like. So mass 1, rather weight 1 times Z coordinate 1, weight 2 times Z coordinate 2, weight number 3 by Z coordinate 3, and so on. Everybody understands what happened here?
Yeah.
All right, perfect. So, and see, we know all the numbers. kg0 is given to us here, 7.5. Initial displacement is given to us, 10,000 tons. All the additional masses we know. kg1 is 8, kg2 is 2, weight 1 is 500, the other one is 700. So we all the numbers here are known. So that's a straightforward one. All right, and you do the same thing for computing the, okay, let me just write out the numbers so you know what exactly. So this is 7.5 times 10,000 ton. And again, ton, top and bottom will cancel out. So you can convert it to kg or leave it like this. Plus 8 times 500 plus 2 times 700 minus 6 times 200 minus 1.5 times 100 over 10,000 plus 500 plus 700 minus 200 minus 100 and whatever number you get here. Okay, same way we compute the y coordinate of G final is CG0 delta 0 plus CG1 little g delta 1 plus okay. So this should be CG1 here. I'll tell you why. So let me write out the full thing. CG2 delta 2 minus CG3 delta 3 minus CG4 delta 4. Okay, the reason I wrote CG1 here is because our initial state was already tilted. So I should put down the CG1 value, not the CG0 value. Okay, that's why I put CG1. And that we already know, CG1 is basically, this is equal to G0, G1, which we computed. All right, and again, you just go to the table and plug in these numbers, then you get your y coordinate. Once you have this z coordinate of G final, this basically gives us, and this is equal to kg final. And this is equal to cg final. Okay, remember, when we talk about lateral, we start at the center line. When we talk about the vertical, we start at the keel. Then to find phi final equal to tan inverse this is unknown right now. G final m is unknown, but this is basically equal to k m minus k g final. And that's it. You have everything you need. You'll end up with, the answer you'll get is 4.9 degrees. So procedure-wise, any questions? See, it's the same thing we keep doing. Y1, M1 plus Y2, M2 plus dot, dot, dot divided by total mass. Okay, so again, don't hesitate. Ask me anything you want right now. I don't like it when you leave everything. I'll figure it out during the quiz and then you run out of time. There's no point doing that. Ask me right now.
That makes sense.
Anybody want like a quick rerun? All right.
Will there be an example where it's not like a rectangular hull?
Oh,
We'll
so
have-
for the example we just did, we're not told it's a rectangular hull, right? Yeah, so let me just bring back the example. We're just told we're subtracting some weight from a hull. We're given the initial weight, we're given the initial values. We're never told it's a rectangular hull. So here you don't need to know the geometry of the hull. All you need to know is the mass loading and where you put the mass.
Okay, I see. Yeah.
Yeah, if we were not told G0M, then we would need to know the geometry of the hull because there we need an eye, we need a nabla, etc. So we're fortunate that we were given G0M. We were basically given the meta center location. If we don't know the meta center location, then yes, we would have to compute it. Okay, any other questions? All right, perfect. So I would have told you about free surface effects next, but I think we have 20 minutes, which is just short of what we need. So I'll tell you other things. Before that, any questions about homework? I think with all these examples, you should be able to do it now.
Can you tell us a little bit about the format of the midterm?
The format.
Well, how are you going to do it? For instance, how much time are you going to give us? Are you going to email out the midterm, et cetera, like you did last time, or?
Yeah, exact same thing as the quiz. You'll have the whole class period to do it, and whoever is here will get it via email. If you're not here, you won't get it. So everybody should be live in class. And it's open book, open notes. You need to have your webcams on. Any other questions?
Can we use notes off our tablet again?
Yeah, so you can use notes on your tablet, but do not access the internet at any time. Do not access the internet, meaning do not search for anything. You will be live at that time anyway. All right, okay, so let me tell you about Tpc and Tpi. So anytime you have to deal with designing a hull or naval architecture in general, you'll encounter these terms. So where's the hard break? Tpc and Tpi. And the abbreviations are basically this ton force per inch. We will not deal with TPI. We will stick to the standard units, TPC. So this is ton per centimeter. And just as a reminder, 1 ton is equal to 1,000 kilograms. All right. So TPC and TPC is defined as the weight or mass required to change the existing waterline level by 1 inch in the case of TPI or 1 centimeter. If I draw a generic hull, so let's say this is so if a hull were floating at the waterline shown in blue, and we add extra weight and the water, or we subtract or add extra weight and the waterline changes slightly, you can basically figure out what's the volume change in the waterline. Okay. If you know the cross-sectional area, you just multiply that by 1 centimeter. Of course, since the cross-sectional area keeps changing, that will not be the exact volume. But if for very small changes, the cross-section on top versus the new waterline, the difference will be very small. So we can assume the cross-sectional area is the same before and after submersion or immersion. For small changes in the waterline, area of the water plane changes by a negligible amount. This we can approximate. To remain constant. And this Tpc or Tpi value is, it's a very useful and very quick indication of how much your water line will change if you take on an extra 10 ton of cargo. So it's a very quick way to compute the new state of your ship. Of course, if you add 1,000 tons, then things will change because you cannot assume a constant AWP anymore. The area will change significantly. All right, so it comes out to a very simple formula, and I'll very quickly show you how we get to that. So TPC is basically asking how many tons needed to change the draft by 1 centimeter. All right, so we know we can basically compute the volume change is area WP times 1 centimeter. So one centimeter is 0.01 meter, so that's why I wrote this. That means if I know the change in the displaced volume, I know mass change is basically rho times lambda change. Very frequently, people will give you rho not in kg per meter cube, but in ton per meter cube. But yeah, you just change from one to the other as is convenient. Okay. So TPC is what? So the mass required in kilograms to change the draft by 1 centimeter is this much in kilogram. So in ton, it's basically that kilogram divided by 1,000. So this is M change divided by 1,000 ton. Okay, and this basically gives us rho AWP divided by 100 times 1 over 1,000. If rho is in kg per meter cubed. Okay, So that's a very easy and quick way to compute TPC. You just need to know the area of the water plane and rho of the seawater, of course. All right, any questions? Okay, so that was, yep. No. That was, I mean, if you understand all of what we talked about right now, you basically understand what happens when you load or unload cargo. One thing that happens is your water line will change slightly, and there's a good easy number, Tpc or Tpi, that we use to describe that. And the other thing that can happen is you change the angle of heel or list. And of course, you might even change the trim angle, but we'll talk about that later. Okay. Right, there's one more thing. Yeah, we have 5 minutes, so we can start this. So if you have suspended weight, right? What I mean by suspended weight shift is on these huge cargo ships, you see there's an onboard crane, which basically you attach the container to, it lifts it out of the hold and dumps it on land. Or if the ship is not large enough, it uses an on-land crane. So the crane is suspended over the ship, attach the cargo, again, lift it out. When you do these things, you change the static stability of the ship significantly. The reason is, first thing, you are shifting mass. So again, these angle changes will happen, and you need to make sure that it doesn't exceed your requirements. And the second thing is, if you have an onboard crane, you are basically moving as soon as it lifts the cargo up from the floor, you have shifted all of your weight from the bottom, the hold of the ship, to the top of the crane. So that's a huge disadvantage. Remember, we don't want the center of gravity to be so high. So it can, if you don't design the ship correctly, it can actually capsize. All right. So e.g. onboard crane. So let's consider a weight W. Suspended freely from a point H vertical above the center of gravity. And let me draw a sketch of that. let me say my crane is located here and with its containers hanging from some cables at this loading point O. And this, it's basically, you've created a pendulum now. So this cargo can shift slightly from side to side. This location we'll call G1 and that location we'll call G0. All right, and then we're told this vertical distance is H vertical. And the weight is little w. Okay. So G0 is before your crane was in operation. And as soon as this leaves the surface, G0 will change. What will happen to G0? We're out of time, so let's talk about that next class after your midterm. Any questions? Any remaining questions about midterm? Okay, topic coverage is homework 1, 2, and 3, except the question 2 from homework 3. I sent an announcement about that. So we didn't talk about free surface effects. So leave that one out. All right, so yeah, I'll grade your quiz this weekend and good luck for your exam.